So let's get started. So at first, thank you so much for IEEE AtC-AtG conference committee, especially Nivedita, Pankaj, and everyone else who uh, worked so hard day and night to bring this all together. So as Sophia mentioned, that I'm Sonal Shreya from Aarhus University, Denmark, and today I'm going to talk about that from magnetism to mind. So how physics-informed framework for next generation brain inspired computing can be designed and developed. So although Sophia has already given my introduction, but I will just briefly walk through my introduction. So I have done my PhD from IIT Roorkee in India. Then I was a postdoc candidate at Aarhus University, and from past 2 years, I'm working as assistant professor at the same university. Currently, I also acquire a role of chair of IEEE Women in Engineering, vice chair of CAS Society. I'm also Women in Magnetism Committee, and these are some other courses. And then my research area is spintronic, device modeling, neuromorphic computing, integrated CMOS and spintronic design. And I teach digital circuits, semiconductor devices, and also introducing a new course on spintronic next semester. So this is Aarhus University, and it is a very old university. Soon we are going to complete 100 years, and we are very well mix of national and international students here. This is where is our IT park. So I'm sitting somewhere here at the moment. So this is my department. These are some of my activities that we carry out to boost our research work and meet more people and collaboration. So these are some research day which happens at our university. We also host Women in Magnetism Leadership Workshop, which is annually happens. And this year it is going to tentatively on December 1st week. So soon you will hear about it more. Then this is conference from Neuroscience Academy in Denmark. These are some activities from Women in Engineering Denmark, and these are some presentations and poster presentation at MMM and Intermac conferences. And we are also very actively engaged in several other kind of collaboration and networking platforms at Aarhus University through IEEE chapters, sections, Optica, Chip Competence Center, Digit, and so on and so forth. So before I start, I would like to share that as of now, most of us already are well aware of our journey from sand to a chip, that how just from commonly available sand, we extracted the silicon, then we built the silicon ingot, then converted it into wafer, and then developed a silicon chip, which nowadays we see everywhere in our electronic gadgets, electronic devices, so on and so forth. So if we talk about in semiconductor industry, then it is not only focused on the hardware, but it also consists of the software. And if we see closely, then there are several LLM products and we can say software developing so fast in past few years. For example, ChatGPT, Gemini, Copilot, Cloud, etc. Whereas hardware industry is also putting a lot of effort to keep up the pace with the software. For example, Intel, Nvidia, Qualcomm, Samsung, Apple. So they are working hard to bring the AI, to develop the AI industry, and both in terms of hybrid, where we can minimize the dependence on the cloud AI. And also, we know that there are huge gaps when we talk about the hardware and software, because the hardware industry is not matching with the pace of the software development. So, what can we do? Should we focus on more on hardware software co-design? where algorithm and training is something which can bridge the gap. That means that we need to develop more on-chip training programs and algorithms, and even architectures, engineer them in the way that we can reach to our globe, our requirement and goal. But if we see the energy crisis that we are facing at the moment, so for example, if we take the example of ChatGPT 5 or any other LLM Gen AI platform, then we should be aware that just to get one prompt of response, what we give, we have to spend at least 10 times, up to 10 times of our mobile phone full charging. So you can imagine that how much energy it is consuming. And as we can also see that we are now far away from our conventional laws, for example, Moore's law, which says that it doubles in every 24 months, then Dinard's law and all the other laws. On the other hand, if we see the energy production global, then it is increasing also with a very fast pace. And we can see that if we keep going on with the targeted system, benchmark system, then soon we are going to hit the wall of the overall world energy production. Whereas if we work now on developing new hardware and invest on new material and devices, then maybe we can bring it down and delay the energy crisis that we will soon acknowledge. So we can also see a trend that from past 2 years, the Nobel Prize is also giving us an idea that where we are at the moment. So, for example, 2024 Nobel Prize was given to these two scientists who introduced the machine learning algorithm for artificial neural network, and they were the first of the scientists who talked about specifically, if I name Hopfield neural network, which we now today call it. And they talked about the energy minimization technique, and then how the physics can do the computation. Then following, if we see the 2025 Nobel Prize in Physics, then also we can see that they got the prize for introducing the macroscopic quantum in chip. So it means that we are not only assuming, but we are now already living the paradigm shift in computing. The focus should be more on novel materials and devices. And then because our brain is a physical system, it is not an electronic system. So we need to see more on the physical system property. So we need to look into that, how the materials can do the computing itself, and then how we can bring the physics into a chip. Now, there is no need to mention that, of course, we are surrounded by semiconductor industry everywhere. AI is today everywhere. So just to take a few of the examples. So first of all, smart camera, so surveillance. So before, if we look back 10 years ago, then camera was not smart. So it will not sense the movement or the sound, but today, if we see that the smart cameras are very sensitive, and then they are smart, they can move, they can sense what are you talking, they can record. So there is a lot more that is happening. Then second example is autonomous or self-driving, which is again surrounded by several kind of multifunctional chip. So from sensors to storing to processing, and all these kind of chip are already there. Then another good example is AI robot vacuum cleaner, where we just give them some mapping of the room, and then it itself is taking decisions that if what kind of object is in front of it and how it is doing the cleaning and everything. And then last example is that we are doing using not only every minute, but I think every few seconds that we are using our AI assistant. Neuromorphic computing is no longer in the lab now. It is already embedded in the devices that watch, listen, and move in our world. So it means that they are able to mimic the spikes functionality, which the way that how our brain works. They process the signal. They are smart. So, for example, some of the neuromorphic computing chip are Intel Lohi, IBM True North, and Brain chip. But do they rhythmically learn continuously? Do they adapt? So, for example, if vacuum cleaner, we have mapped it for your living room. So, without mapping, will it work at some outside environment? So, for example, if you put it in the lawn, then will it work in the similar way as it was working in the room? Then decision in certain environment. So similarly, the same thing that if the environmental, so for example, I live in Denmark, so here is the weather condition is so harsh. So the AI model or AI chip that is trained for certain temperature, and then if you see the temperature change from in summers from 30 degrees to minus degrees, and accordingly several other factors, then will it adapt accordingly? So then we need to think more that how we can actually build brain inspired computing. So here in my hand, you can see this is a brain of a pig. And then the idea is that we need to see that how we can bring this brain into a computer and computing chip so that we can focus on not clock based computation, but spike based parallel plastic. So the synaptic plasticity we can incorporate in our computing chip. It can be analog as well as digital. Then it can have the property of stochasticity. It is not the conventional von Neumann architecture, but has in-memory computing, and it is more energy efficient. So this is a simple difference between the neuromorphic computing and the von Neumann architecture. So we are very well aware of that in von Neumann architecture, the CPU and memory are separated, whereas in the brain, neuromorphic architecture, similar to our brain, the neurons and synapses are co-located. And then if we see the difference in their operation, so most of this we already know. And there is something that now we need to also add in the features that we need to add into neuromorphic computing is that it needs to become a multifunctional as well. So for example, it should not only do the storage and computing, but it should also be capable of communicating, sensing, and the secure. It should be secure. So neuromorphic computing, how can we build? By incorporating or studying engineering in memory computing, learning, make it on-chip learning, not only unsupervised, supervised reinforcement, then make it power efficiency, because as you all are aware that our brain can consume only 20 watt of power, whereas supercomputers still are consuming megawatts of power. Then it should have massive parallelism and then complex computing. So it should be capable of doing complex computing. But then the question comes that is our conventional CMOS electronics is capable of doing this functionality? Because still all the, for example, Intel Lohi and IBM True North, they all are still using CMOS technology. But the challenges are that they are very bulky in size, unable to match the AI energy demand with minimizing the technology node. It needs more and more data center because it do not have the inherent property of in-memory computing. We need to do the engineering and build the circuits in a way that it can do the in-memory computing. And then as we are scaling down the technology node, more and more heat is dissipated. So let's see some more factors, and then we'll move to the magnetism or spintronic. So if we see human brain, then we just need to map that how nerve cells are can be mapped with the memory chip. And in that, as we know that there are two main components, the neurons and synapses. So if we use some memoristic technology, then we know that crossbar array is the most popular architecture, which matches with the biological synaptic connection. And then how these layers are connected together to build a neural network. But that is not only the factor that we need to take care. If we want to develop a neural network, then we should also be aware that there can be several kind of neuronal functionality. So for example, a neuron can behave in oscillatory fashion. It can behave, this is the most conventional neuron, which is Hutchinson-Huxley neuron model. So which can work on the capacitive and resistive based model. And then it can have a spiking neuronal functionality, which the most popular one is leaky integrate and fire neuron. And then based on each of these neurons, the design of neural network will also vary. So for example, from oscillatory neuron, we can build oscillatory neural network. Similarly from LIF, spiking neural network, stochastic neural network, and so on and so forth. And then if we want to develop a brain-inspired computing, then we should also be aware that our brain is not one or two single functional device or machine, but it is doing a multitasking at the same time. So for example, if now I am speaking, then I am looking also. I am if somebody will speak, then I'll hear also. So we need to also think about that how to make the multisensory fusion. And then only we can go forward with the application, which can be neuromorphic computing, brain machine interface, artificial perpetual systems. Now coming to some of the emerging devices. So these days, this is not the only four classification, but there are several more. So I will just go through these. So for example, spintronic, which is based on magnetic memory based technology, resistive. So it can again contain various other materials, but here it is just showing that how the filament is formed, and then based on its low and high resistance states, the memory is designed. Then similarly, ferroelectric memories, where the ferroelectricity and property of a device of the material is harnessed to do the in-memory kind of functionality. And then similarly, phase change memory, where the material property that is amorphous or crystalline work together to form the similar kind of functionality. Then the second thing is that we know that for biological bio-inspired computing, the main two components are synapses and neuron. But we should also be aware that these are not two separated components, but they are interconnected. So when we are designing artificial neuron or artificial synapse, so that is not the correct way, but we need to think always from a perspective that we need to develop a spiking neuron, so which itself consists of the synapse. And then if we see that there can be different properties of both synapse and neuron. So for example, the synaptic properties can consist of synaptic delay, excitatory and inhibitory property, short-term plasticity, long-term plasticity, spatiotemporal, which is usually used in reservoir computing. Similarly, for neuronal properties, it can be integrate and fire. It can be periodic spikes. It can be a spike number based on adaptation. It can have a periodic bursting property, burst number adaptation, and it can have oscillatory property, based on which, if whatever synaptic and neuronal property we choose, and whatever material or device we are working on, then accordingly we need to model the device and then develop the neuromorphic computing system. So if we focus on spintronic, or to say magnetism, then we know that here we harness the two state variables, which are the spin up and spin down property of electron instead of the charge based property. And we also know that there is a possibility to switch the magnetization of a spintronic device or material from one direction to another direction. So, what Spintronic is offering to build a brain-inspired computing? First is that it has a sub-femtojoule switching. Memory and compute in the same device is possible. Near zero standby power, scalability to sub 10 nanometers. So it means that this aligns with the brain's energy efficiency and memory-centric architecture. In early days, when we talk about introducing a new device, then device modeling was the first step to take into, apart from the fabrication of the devices and characterization, because this was the way to bridge the gap between the process developers and IC designers. So for specifically for spin devices, then we could have focused on a macro spin model, micromagnetic model, and then make it more physics-based analytical model, so which is still our focus now. But the focus has a little bit shifted towards that we need to develop more physics-informed and data-driven models for futuristic electronics. And then also, in order to bridge the physics and chip, so that is magnetism to mind, we need to go have the bottom up approach. That means that we need to go into the atomistic level, the material parameters, formation of the devices. So we need to look into an initio atomistic and micromagnetic model to understand the property of the materials. Similarly, on device level, then we need to do the device characteristic to see that if we are able to emulate the neuronal or synaptic functionality, then accordingly develop the neuron circuit and then the neural network system. So this is a simple steps for modeling of a spin device. Here, the example taken is a voltage controlled spin orbit torque MRAM. So if we have a device and then we do the electrical modeling and then solve the whole bunch of equations and then do the analysis. Similarly, for spin torque nano oscillator, because it has the dynamic property, so then accordingly we do the validation. And then we can also develop the model for multi-level MRAM properties. So if we see the MTJ, that is magnetic tunnel junction, which is the basic building block of spintronic, then it comes with several properties or several features, we can say. And then it can mainly be divided in two parts: switching property and oscillatory property. Then again, it can have from switching, we can attain storage property in memory computing, sensing, and neuromorphic computing. Similarly, from oscillator, we can achieve the different properties. And then based on this, then we go forward with what device we want to choose and what kind of functionality we want to attain. So for brain-inspired computing, always the first step should be to do some compute in memory kind of functionality, that you need to understand that how you can incorporate computing in the memory device. There are some examples. For example, for digit recognition, binary neural network can be designed by the synaptic crossbar array and neuronal activities. Similarly, pattern recognition can be done through some computing logic operations. So for example, XNOR logic gate, then we can recognize the given pattern. Then neuromorphic computing system, where we again connect the crossbar array and then based on the weighted sum, we see that if neuron is fired or not fired. Then there are some recent work on granularity of the spin nano oscillators, where the material itself has a property that it can contain grains or domains, which can each domain or grain can can function differently, can have non-linearity in their electrical properties, for example, in resistance or in frequency. Then they have some short-term memory, the way that the relaxation happens for magnetic vortex. So we did some measurement to identify the vortex state, and then developed reservoir computing. And then based on that, again, if we talk about the physics behind the device, so the physics behind the device to develop the reservoir computing for waveform classification is that the energy minimization, that how the energy is minimized in different grains, and then it was used for identifying or classifying the square wave and sine wave. Then similarly, the one of the our recent work is oscillatory neural network. So where we emulate that two neurons, how they can have a rhythmic synchronization together, and then we develop the basic neural circuit, which consists of two oscillatory neurons connected by a synapse. Then based on that architecture, we did the noise denoising an image. So a noisy image was given, and then based on the synchronization of two neurons, then the image was denoised. And as we see that scalability is still a very challenging aspect to develop such neural networks. Then spiking neural network, where as we know that based on the given pulse, and then it has some leaky and integrate property, and then when it reaches a threshold, and then we say that it spikes, so a neuron is fired. And then based on that, when we design a brain-inspired, bio-inspired neuron, then the input will be the pulse, then accumulation, so how it is accumulated in synaptic weight. Then membrane potential can be a threshold, which we can define, that how we are defining the threshold. And then if the threshold is crossed, and then it is a leaky integrate fire neuron. So these are some classification of...
I have 2 more minutes.
Yeah, sure. Thank you. So how through gradient driven skyrmion, which is again a magnetic property of spintronic device. So using strain gradient or DMI gradient or anisotropy gradient, we can attain this type of leaky integrate fire neuron. Where based on the position of the skyrmion, so if you see here that this is a nano track, and then suppose if our skyrmion detection point is 20 nanometer from here, from the start, and then it can fire whenever the skyrmion reaches this detection point, that is 20 nanometer. And then we have the output spike. So this is again explained here. But still, then we know that neurons do not fire in single uniform pattern, but it can have adjust their firing mode depending on the task, the input strength, the brain region, and various states such as attention, sleep, stress. So can we build a reconfigurable neuron? So my students will, just after my talk, will be presenting because this is something that currently we are working on, that how to develop a reconfigurable neuron. And now coming to my research facilities. So because I'm building a new research group also at Aarhus University, Denmark. So we have these facilities, and I'm also introducing a new course, Applied Spintronic for master degree. So with this, I would like to leave you with this vision that if you want to develop various kind of applications, the way that how our brain works, then start working on these steps, that material investigation, device, neuronal circuit, neural network, and then reach to whatever goal of application that you have. So these are my students. I have two PhD students, and one is visiting, who has now not in Aarhus University, but went back to India, but he's still working on some work. Then I have two master students. These are so far my main collaborators, and I have various other collaboration as well globally. So thank you so much.